All right, everybody. I'm here to talk to you today about a feature that I am proposing to C++, constexpr function parameters. But before I get into that, first I want to talk a little bit about who I am. My name is David Stone. I am a software engineer at Uber, where I work on autonomous vehicles. And I'm also a member of the C++ Standardization Committee, where I chair the module study group, and I'm the vice chair of the evolution working group, which is the group that new language proposals have to go through. So today, I'll go over briefly how constexpr works today. Then, what am I proposing? Where is this in the process of standardization? And other related work. If you have any questions, feel free to raise your hand throughout. You don't have to save them for the end or anything. I'm happy to kind of take them as we go. I don't want you sitting there in the audience being confused by anything I'm saying. So first, how constexpr works now. There are two types of constexpr in C++. There's constexpr on variables, which looks like this. You declare a variable with constexpr, and then you can use it in any context that requires a compile time constant. For instance, you can use it as an array bound. You can use it as a template parameter. You can use it in a static assert. It's fairly straightforward. The more complicated constexpr in C++ is constexpr on functions. So here we have a function that is declared constexpr. It accepts a double, returns a double, and it returns the inverse. And if you try to divide by 0, it throws an exception. So if you take this function and you use it in a context that requires a constant expression, you'll get a compile time error because you're not allowed to throw a compile time. If you use it in a context like that second line there, this runtime computation, and you give it some runtime value, that works just fine, and this function will just be a regular C++ function at that point. And if you pass it a compile time constant, but you don't use it in a context that requires a constant expression, then you'll get a runtime exception thrown, because this will not actually be evaluated at compile time. So the difference is that constexpr variables require compile time construction and destruction, whereas constexpr on a function merely permits compile time evaluation. Essentially, if everything that it does can be done at compile time following the rules of a constexpr function, and you use it in a context that requires a constant expression, it will be. Otherwise, it won't. So I mentioned some things that a constant evaluation cannot do. And we've really shortened this list a lot as C++ has progressed. In C++ 03, there was a small number of things that you could do, and now we have a small number of things that you can't do. And you can kind of group them into a few categories. So one thing that you can't do at compile time is read values that are not constant expressions, call functions that are not constexpr, or are not defined. That makes sense. You can't take a runtime variable and use it at compile time. It actually needs to be compile time all the way through if you're going to use compile time. That's a reasonable restriction. You also can't use volatile, which is the same sort of idea. Volatile's meaning is that reads and writes of this variable are an observable side effect. It's used to interface with hardware on your computer, which doesn't really exist at compile time. So that's another reasonable restriction. You can't exceed implementation limits. Basically, just the compiler isn't going to go into an infinite loop at compile time. It has a certain step limit. It has a certain recursion depth. Just sort of things to make sure that your compiler itself doesn't crash or run out of memory or do anything like that. You also can't invoke undefined or indeterminate behavior. For instance, division by 0, integer overflow, things like that. The compiler is actually required to diagnose this undefined behavior for you. And similarly, you can't throw an exception. So basically, the goal here is that we want to catch any sort of error that might happen at compile time, rather than just compiling your program when the compiler says, oh, there's an error here. It tells you that. You also can't inspect the common initial subsequence of a union or reinterpret cast or cast from void star. Basically, you can't do things that would get you the object representation at compile time. And then you also can't do some things with addresses. We might go into that some more later. We'll see kind of if people have any questions related to that. But it's not too important. Like it's more of like arcane corners of the language that we probably don't care about. So here's an example, kind of make it a little more concrete. Say we have some function, declared constexpr, that accepts a bool. And if the bool is true, we return 6. Otherwise, we return 1/0. Now, if we call that with true, then that's fine. That's going to give us the value of 6. It's a constant expression. But if we call it with false, that's ill-formed, and the compiler is actually required to give you a diagnostic because you divided by 0. But if we don't assign the result to a constexpr variable, like I said before, it will be evaluated at runtime. So you'll either get 6 or undefined behavior at runtime for division by 0. So that's kind of the background of constexpr. That's really what you need to know about how the language works right now to understand the rest of this proposal. So the proposal, you can see the latest draft of it on GitHub. There's a link there. I'll be attaching it to the CppCon schedule, so you don't have to write this down if you want to go look at it. But the basic feature is this. I'm proposing allowing you to declare a function parameter as constexpr. And you can use that value any way that you can use a constexpr variable or a template parameter now. So inside the body of the function, you can say static assert on the value, and everything is fine. So that's the core feature that I'm proposing. Then an additional thing is I'm proposing adding a new function is constant expression. You give it an expression, and it tells you, is that a constant expression? And it turns out that it's not actually possible to write this in C++ today generally. You can write an is constant expression that works in some cases, but not others, and the reasons for it are really strange. Sometimes you can determine if something is a constant expression if you use brace initialization because it has to check whether it's a narrowing conversion. But you can't actually do that in every context. So for instance here, if we say static assert is constant expression, the string literal awesome, that'll pass because the string literal is a constant expression. The next thing that I'm proposing as part of this is the ability to overload on constexpr parameters. So if you have two functions f, one of them takes a constexpr int, the other one takes an int, then you will call the correct overload depending on whether you give it a compile time constant or not. It's really helpful. And I'll go into some details of exactly why you would want this ability, the sorts of things that it allows you to do that you can't really express today. The final thing that I'm proposing is maybe constexpr. And I have here, it's a straw man syntax. I'll later on go into the syntax I'm actually proposing. Before we can actually understand how we should spell this, what it should look like in your source code, we have to understand a little bit more about what are the semantics that I'm proposing, what is the mental model that you're supposed to have. And I don't want to bias anyone in favor of a particular syntax that I just kind of put up there as one of the options. So right now, I'm using a very obviously not real syntax proposal. Sometimes in the past, we've kind of just put in a placeholder syntax and said, oh yeah, we'll get to that later, and figure out what the real thing is. And then we end up with stuff like, I don't know, reflexpr. So I want to make sure that naming is really important. And it's actually kind of a theme of this presentation, that the way that your code looks, the way that you write things, actually affects the way that people think about it. And so we want to make sure that we give people a way of writing something that matches the model that we want them to have. So we'll kind of get into exactly what syntax should go here a little bit later. So I want to talk a bit more about what are the design goals of this proposal. Why am I trying to solve the problems in this way? What are the things I'm trying to solve at a high level? First of all, consistency. The title of this presentation is Eliminating Metaprogramming from C++. And what I mean by that is we have metaprogramming, which is a completely different type of programming than regular C++. How many of you have ever done metaprogramming? Okay, most people. How many of you feel comfortable doing it at work? Okay, slightly fewer. How many of your coworkers feel comfortable with you doing it at work? Very few people. And I think that's a problem because like there are some good things to it, but just the fact that you have to do it differently from everything else kind of scares people off. One of my other goals is to improve performance. There are certain things that my proposal will allow you to write that you can't write today that help C++ continue to be the high-performance programming language. And the final design goal that I have is improving diagnostics. Right now, as a library author, there are bugs that your users have that you can't catch. And you know they're there, and you can look at the source code, and the compiler knows that they're there, but just because of the way that the code is structured in the rules of C++, you actually can't tell the user that they're doing something wrong. So I work at Uber, as I said, on autonomous vehicles. And I care very much about the rules of the road. It's something that we have to focus on a lot. And lots of people think that the place they live has crazy drivers. But let me tell you about a little place called Discordia. In Discordia, the rules of driving they're a little bit different than you might be used to. Now, it's important, I think, to have consistent rules, not just a set of rules that cover every situation, but you want those rules to actually be consistent so that people can understand them. In Discordia, they don't believe that. In Discordia, on the east-west streets, the traffic lights are the way you're used to them. But on the north-south streets, red means go and green means stop. And everyone who lives there says, oh, no, that's fine, that's fine. Like, you know which road you're on, you can figure it out, it's not a problem. In Discordia, on Tuesdays, you push the brake to go faster, and you push the gas pedal to slow down. But that's okay. Like, you get in your car to start, you push the wrong pedal, the car doesn't go, you push the other one, it's fine. Like, you get used to it. On Friday nights, semi-trucks drive on the left side of the road. But nobody drives on Friday nights anyway, so it's not a big deal. I think that is a big deal. I think that having inconsistent rules that change depending on things that really shouldn't affect what you're doing are a bad thing. And that leads me to the fundamental principle behind my proposal, and that is no shadow worlds. Malte Skarupka wrote an article titled No Shadow Worlds a few years ago, and he got the idea from a guy named Gilad Braka. The central idea is that a shadow world is a part of a programming language that is segregated from the rest of the language. It's something where when you're working in it, you wish you had the power of the full programming language, but you don't. C++ has no fewer than 4 general-purpose shadow languages, or programming languages, I should say. There's regular runtime C++, but then there's 3 shadow worlds. There's constexpr C++, templates, and macros. Now, what I find interesting is that there's a long history of people recognizing the concept of shadow worlds and then falling victim to them without realizing it. So I mentioned Malte Skarupka wrote an article about an article written by Gilad Braka. Now, Gilad Braka was talking about kind of the importance of recognizing this and not introducing shadow worlds. But then in his article and in his presentation, he was talking about a programming language that introduced a macro system that was a shadow world. And Malte Skarupka was writing about this, and he noticed that. And he said, I have this idea for programming language of no shadow worlds. We need to eliminate macros from our programming languages. And what that means is that we have to have a powerful template system. But in my mind, the template system is itself a shadow world. Like, this is a really difficult problem. It's really easy to accidentally constrain yourself into creating something new in a small corner of the language without realizing it. So my goal here is to try to find a thing that will be consistent with the rest of the language, that will sort of align with things and fit into existing things rather than being a completely new thing. So we have, as I mentioned in C++, constexpr. In C++ 11, it was a really limited shadow world. you could hardly do anything. A constexpr function basically had to just be a return statement, a static assert, or a type def. There were no ifs. There were no fors. So that meant that when you were writing code in constexpr C++11, there was lots of recursive code with a ternary conditional. And like, you could get used to it, just like you could get used to red means go and green means stop. But, you know, it was always a little weird. C++17 expanded constexpr in 14 and in 17. But we had no memory allocation. We had no destructors. C++20 lifts that restriction, and now we can do almost everything in C++17, or in C++20 rather, at constexpr, except for that list I mentioned at the beginning. And that's a really short list. Like, we're kind of recognizing this problem and starting to fix it for constexpr. We're generalizing constexpr more and more to have it be able to be just normal code that you write. And then macros. I think we're all aware of the problems with macros. There's no loops, no mutation, almost no recursion. Turns out there actually is a way to kind of fake it, but it's really ugly. There's no scoping. There's weird if statements. I don't think I really have to go into a lot of detail about the problems of macros. But for this presentation, I'm actually going to be focused on templates. Templates are the shadow of functions. The compile time parameters are lexically split off from the other parameters. So if you want to pass a compile time parameter and a runtime parameter, you have to say something like f open angle bracket 0 close angle bracket open paren 1 close paren. And that might seem fine at first. But then you realize that there are a lot of things that templates can't do. You cannot pass template arguments to constructors. You can't pass template arguments to overloaded operators. You can't overload on whether a value is known at compile time. You can't put a compile time argument after a runtime argument. Regardless of how you want to write your function, if it's a template parameter, it goes first. You can't forward a pack of arguments, some of them known at compile time, and some of them known at runtime, without having two different parameter packs, and you have to know that the function you're forwarding to has this requirement. So the reason I have this proposal is because of Loki, MPL, Fusion, HANA, Meta, Brigand, Simple C++ Metaprogramming Library, Turbo, and many others that I don't know about or I've forgotten. Larry Wall, the creator of Perl 6, said, when they built the University of California at Irvine, they just put in the buildings. They did not put in any sidewalks, they just planted grass. The next year, they came back and put the sidewalks where the trails and the grass were. And we see here what happens if we don't do that. If we build people a path that is not the path to where they want to go, they're going to make their own path that goes there. My proposal is that we should pave this path. So I'm going to give you a few examples of the types of things that we have to do today and the types of problems that we face because we do not have this ability to have a constexpr function parameter. So here we have arrays. You index them with the bracket operator. That's the syntax we're familiar with, we know and love. If you index it with 0, it's fine. Index it with 1, it's fine. Index it with 2, undefined behavior. The compiler can clearly see that what you're doing is wrong, and maybe your compiler has implemented a custom warning. I don't believe any have for standard array. And then we look at tuple. And what is tuple, conceptually? I believe that tuple is essentially the same type of thing as array, except the types can be different. But the syntax doesn't reflect that. You have to say std : get, and then put the index in angle brackets. That was the syntax we made up for C++11, because we added tuple. Because the bracket operator couldn't work, because you can't pass a template parameter to an overloaded operator. And with tuple, you can index the first two values, and it's fine. And then you index the third value, which doesn't exist, and you get a compile time error. So we have the syntax we want on one hand, or the semantics that we want on the other hand. With my proposal, it could look like this. We can have a compile time error for indexing an array out of bounds with a constexpr value. And we can have the nice syntax for indexing a tuple. How many of you have used TrueType? Okay. TrueType is, it was added in C++11. It's part of type traits. It is a type that encodes the value true. This is what I think true should look like. Integral constant is even worse. We have integral constant, which encodes an integer value in a type. There's been a proposal to just shorten that to constant, now that we have class types as non-type template parameters. And then someone realized, hey, we can just deduce the type. You don't have to specify it, so we can have constant and then just some value. We can encode arbitrary values in types. HANA has int underscore c following the lead of MPL int underscore. More ways to encode values in types, but trying to get the syntax a little bit shorter. And there's a bunch more I don't know about. This is what I think the number 24 should look like. Louis Dion, the creator of Boost HANA, said, if we have constexpr parameters, I don't think there's much purpose for integral constants anymore. Major parts of HANA would be significantly more intuitive to use that way. This is what code using HANA looks like for the person writing the function. You say, I'm going to accept a value of type HANA int underscore parameterized on the actual value, but I don't care about that. I care about that value in there. But the reason you have the syntax is because that function syntax is so powerful. You want your users to be able to just call regular functions. Under my proposal, it would look like this. Conceptually, the thing that you're trying to say is, I want an int, and I want it to be constexpr. And this allows you to directly express your intent. This is what it looks like on the caller side. If they haven't already wrapped up their integer type in one of these things, they have to do something like this. I think it should look like this. C++20 adds the spaceship operator. The comparison operator, a single operation that returns whether two things are less than, equal to, or greater than. And when you use the spaceship operator directly, which should be rare, but when you do, the intended use for it is that you compare it against an integer literal 0. So you say left-hand side, spaceship, right-hand side. If you say less than 0, then you're saying left-hand side is less than right-hand side. If you say equals 0, you're saying the two are equal. And if you say greater than 0, you're saying that the two are greater. The left-hand side is greater than the right-hand side. This is valid, but due to kind of a glitch, I guess, in the language, it's defined as an unspecified comparison type that accepts an integer literal 0. But it turns out in C++ there's only one type that has that property, and that's nullputter t. So you can also compare the result of a spaceship operator in your implementation, most likely, with nullputter. This was never intended in the design. We knew that it was possible, but there wasn't really anything we could do to prevent it without adding even more stuff into the compiler. And I think part of the problem here is twofold, really. One is that this feature cannot accept that right-hand side parameter as a constexpr int and just require it to be 0. And second, we can't define types like nullputter t that can only be constructed from a subset of integer values. We can only operate on types even if the value is known at compile time. But this was a property that we found so useful that it's actually existed since C. The ability to say the integer value 0 is special for this type. And I think that built-in pointer types are not the only type that have this property, where they care about a particular value as being special. So under my proposal, we could have this. If you try to compare against nullputter, which is not intended to be supported, you get an error saying you can't compare. That should say operator less than, not operator equal equal. I'm happy. Okay, so how many people, by a show of hands, think they know the rule for when you need to use type name in template code? Okay. How many people think they know the rules for when you need to use template? Much fewer. Okay. So sometimes this is the code that you write, and sometimes this is the code that you write. And the reason for that is that without the template keyword, what this looks like to the compiler is c.f less than n greater than a parenthesized x. And that's syntactically valid. So you need to put in a template keyword there to say, actually, no, c.f is a member template, member function template. And n is a template parameter, and x is a regular parameter. I think that's crazy. Like, we have a room full of people who are really passionate about learning about C++. And I ask, how many people know how to call a function in a template? And most people don't raise their hand. Because it doesn't look like this. Like, this is really the thing that we're trying to express. We're trying to express, I have a function, and it takes 2 parameters. And the first one is known at compile time. regex. So this regular expression in, I believe, all popular standard library implementations is going to be exponential time with a bunch of A's and B's. If you have a string 100 characters long, then it's going to take about 2 to the 100 steps to realize that a bunch of A's and B's don't match this regular expression. It's possible to work around this. It's possible to avoid this problem. But doing so is valid only for some types of regular expressions. If you have a back reference, then we don't know of any way to do better than exponential time. But there are no back references in this regular expression. It is theoretically possible to construct a regular expression that uses linear time and linear space to parse this rather than exponential time. But that would require the regex implementation to do 2 scans of the input string always, and have some sort of variant type in it that stores, do I have this DFA, this finite automaton that I built up, or do I have the backtracking implementation? You'd have to have some sort of way of switching on those, and you'd have to pay the cost all the time. So with this proposal, same regular expression, most regular expressions are compile time constants. This is the idea behind Hanna Duzakova's CTRE library, the compile time regular expression library, that if you know the regular expression string at compile time, then you can actually do some really amazing optimizations. You can compile this code down to like assembly instructions that you could just print out on your screen, or like a couple of pages. Like it can be like really straightforward code that is exactly the code that you would handwrite to match the string. But you have to know the string at compile time to build up these structures. And if we had constexpr parameters, we could do that a lot easier. Regular expressions also have a syntax that sometimes confuses people. This is not a valid regular expression. Some people are used to the glob syntax. I think, okay, I'll put in a star. It'll be like in my bash shell. It'll just match everything. But actually, that's not the case. The star is the repetition character. Right now this throws regex error at runtime. But if we had constexpr parameters, we could have a static assert. This says, hey, that star token has to occur after a character that you're trying to repeat. You have to say like .star or something. Yes, Albert.
Would this, the std regex be one of the functions that you said would be a maybe constexpr?
Yeah, so the question was, is std regex something that would be a maybe constexpr? Yes, that would be, I think, how you would do this, so that you can allow people to continue to pass in runtime strings if they are, but take advantage of the extra information if it's known at compile time. So there's a library that I've written called the bounded integer library. Basically, usage of it looks something like this. You define a lower and an upper bound on your integer type, and it sizes the integer appropriately. So you can have an integer from 0 to 10, an integer from 5 to 6, and you can add them. And the type of that is an integer from 5 to 16. And in certain domains, that can be really helpful, of making sure that your integers are exactly as large as they need to be. It can avoid overflow. You can use this to implement essentially a static big integer. You can just continue to grow your integer as needed. You can have an arbitrarily sized integer. But the usage of it isn't always nice. So right now, if you really want to get kind of the maximum performance and the maximum type checking, you have to write something like this. You bring in the literals namespace into your code, which is kind of the recommended way of using literals. And then you construct it. You pass literals to the constructor. But if you forget to do that, then you might get undefined behavior because you're trying to construct an integer with a value that's out of range. So under this proposal, it could look like this. You can just construct the type with just regular integers like you're used to. Now I'd like to talk about a few things that we can't do now, or like problems we just can't solve, or they're so complicated, or so slow to compile, or they have such other bad drawbacks that we just don't bother. For instance, a units library. Let's say we have a value whose type is meters, and we want to cube it. With this proposal, you could just write this code. You can say pow 2 meters 3, so 2 meters to the third power. That gives you 8 cubic meters. You can load in a runtime value of type meters. Say pow that runtime value, where we don't know what the content is, raises to the second power, and then we get square meters, because we know what the type is, because that second argument can be a compile time constant. It'd be possible to write a units library that does this sort of automatic units adjustment with certain mathematical operations. But let's take strlen. Compilers have a built-in strlen function that essentially has a constexpr parameter built into it, or maybe constexpr parameter. Right now, you have to have your compiler give you this built-in if you want to use it at compile time, like we do in char traits length, and if you want to have optimal performance. If you're not lucky enough to have a function like this that the compiler cares about, then you can't do this. You have to say, I'm going to write constexpr strlen, which does the top, but is slow at runtime if the compiler doesn't realize that it can turn it into the bottom at runtime. I think that we should be empowering our users to write the code that they need to write, to work in the situations they need, and to be optimal at runtime, without having to be a compiler writer to do so. Similar example, Intel processors have some AES instructions built in, AES keygen assist. They have also basically implemented constexpr function parameters, but just for this built-in. The function there at the bottom, built-in IA32 AES keygen assist, requires that the second parameter is a compile time constant. If you pass it a runtime value, you get a compile error, but you don't have to use the template syntax. You can just use the regular function syntax, because conceptually they wanted that second parameter to be second. It goes after, the y goes after the x. So why do we need this proposal? It gives us a uniform caller syntax. It gives us better runtimes. We can add compile time diagnostics to libraries. You don't have to change your callers if you find a way to take advantage of the fact that a value is known at compile time while still providing the same interface. It can give you better compile times. If anyone's ever tried to use things like MPL and Boost HANA, they compile pretty slow because every value has to be wrapped in a type, and instantiating a type is one of the slowest things that you can do at compile time. You don't need to reinvent the entire language in a metaprogramming library. HANA has HANA for each. MPL has MPL for each. A lot of these libraries have their own, essentially like pushback and sort and binary search. We have IOTA in the form of make index sequence. We have all of these algorithms by a slightly different name sometimes because we didn't realize it was the same algorithm, implemented at compile time and implemented at runtime. I think that this is why the syntax is important. By changing the syntax, we change how we think about the problem. And if the syntax doesn't match the way we think, then we'll have a hard time really understanding the essence of the problem, decomposing it, and reusing the solutions we already have. We will have to throw everything out and start anew just because we want to use it at a different time in our program's translation or execution. So hopefully you find at least some of these motivating examples compelling. I like to think about proposals in terms of guiding principles. The principles of this proposal are aesthetics, performance, correctness, abstraction, respecting the user's time, and not duplicating work. Don't repeat yourself. So metaprogramming. I care very much about metaprogramming. I gave you an example of the bounded integer library, which is essentially an implementation of dependent types in C++ using some pretty advanced metaprogramming. I'm regularly using cutting-edge features. I am building with Clang Trunk because they have the latest version of a lot of the features I need. And I'm regularly crashing my compiler by using metaprogramming. Like, I'm kind of on the edge here. I care a lot about this. It's really important to me. It's really powerful, but it's the wrong solution. It's the best solution we have. It's the dirt path in the grass. But sometimes it's harder to walk on a dirt path. You definitely can't drive on one. It really slows you down. It can kind of get in your way. It's not the way that we think about programs. So how does this proposal work? Just like a template. So I've been spending a lot of this presentation talking about like why templates are bad. But templates are bad just because the way that you use them is different from the way that you use regular functions. The semantics of templates are really powerful, and that's why we've been able to build all of these powerful things in C++. So what types can be used? Literal types. The constexpr constructor and destructor. These roles have been expanded in C++ 20, allowing constexpr destructors. And also they have to have strong structural equality, which means you have to default operator equal equal, which is a new concept in C++ 20. And all of your bases and members have to have strong structural equality themselves. Basically, the compiler has to be able to easily and obviously determine what it means for two values to be equivalent. This is the same rule as class types as non-type template parameters have. And that's kind of the goal here. We want to have one consistent set of rules for things, rather than one rule that applies to templates, one rule that applies to constexpr, one rule that applies when you're driving north, one rule that applies when you're driving west. Where can you use it? If you have a constexpr parameter, you can use it essentially anywhere after that. This is the same rule again that templates follow. If you have a non-type template parameter, you can use it later on in the template argument list. You can use it in the no-except. You can use it in the requires clause. You can use it in the body and as a static assert and array bound. All of these things are allowed. So now we get to maybe constexpr. That syntax that I've been showing is this to avoid biasing you. But first I want to talk a little bit about the use cases of it. And then we can kind of understand what it should be called. Use cases are the ability to forward arguments. So this is kind of similar to right now when you have forwarding references or universal references. In a template, if you say t-ref, it can be an r-value reference, it can be an l-value reference, and you call standard forward to say whatever it was, keep it that way. The other main use case for maybe constexpr parameters is to have two implementations that diverge in only one area. Because again, remember, the principle of this proposal, one of them, is that you shouldn't have to write the same thing multiple times in slightly different ways. So here we have an example of controlled divergence. This could be a possible implementation of arrays operator bracket. You give it a maybe constexpr index, and if that's a constant expression, you static assert that it's in bounds. And no matter what, you index some secret C array that nobody knows about to make this an aggregate. I think this would be a good use for it, because conceptually you have one function. And if you can use it at compiled time, you just do this one check, but otherwise the body is the same. Overload resolution for constexpr parameters has constexpr basically being a tiebreaker. It matters only for otherwise ambiguous calls, and the types have to be the same. Standardization. Yes?
Why do you need the overload resolution for constexpr, that seems to be a duplicate with the maybe constexpr feature.
Okay, so the question was, why do you need to overload resolution with constexpr? That seems to be a duplicate with the maybe constexpr feature. There are some situations where it's difficult to have control flow. For instance, in a constructor initializer list. You might need to call a function or not, depending on whether it's constexpr in the initializer list, and there's no way to really branch there. So you would then have to wrap it in a lambda and return something from the lambda, which might not even work because you might not have copy elision in that context, depending on what you have to return.
If I can have two overloads of a function, one
Yes.
with constexpr param and the other one without, then doesn't that satisfy the thing that maybe constexpr is trying to do?
Oh, okay, yes. So the question was, if I can have two overloads of the function, one with constexpr and one without, doesn't that satisfy the same sort of problems it does? Yes. All of the problems that can be solved with maybe constexpr can be solved with constexpr overloading, but not always easily. So if we go back to this list, consider the case of forwarding arguments. I want to write a function that accepts some arguments, does something, and then forwards all of those arguments onto another function. If I don't have maybe constexpr, if I have a function that takes 5 parameters, I have to write 2 to the 5 overloads with every possible combination of constexpr on or not on every parameter. And that's basically the same problem that some of us have suffered through in old versions of compilers that implemented move semantics, but not forwarding references, where in place back on old versions of Visual Studio had just 10 overloads stamped out. And that actually led to serious compile time problems. So in a later version, they reduced that number down to 5. And then they implemented variatics, which allowed them to get rid of that pattern. I want to make sure that we don't have that same problem here. I want to make it easy to forward constexpr-ness. And it turns out that you don't want to just deduce that from any template, because that gives you a lot of new template instantiations. All of the existing code that's calling f of 5, f of 6, f of 7 is going to create a completely new template instantiation if we suddenly started deducing it, which would be a serious regression in compile time. So it has to be something that you opt into to kind of avoid that problem. Yes?
Just a quick follow-up. So if you mark a whole function as constexpr, isn't that kind of the same thing as having every argument maybe constexpr?
So the question was, if you mark the function constexpr, isn't that kind of the same thing as having every argument maybe constexpr? Kind of, but not quite. And the problem here is, if this function were just marked constexpr, and there were no maybe constexpr here, I couldn't static assert in the body. You can't treat the parameters of a constexpr function as compile time constants, because it could be called at runtime. The compiler just rejects that and says, what do you mean static assert x is greater than 0? You just said it was an int. It's just an int. That's all it is. I can't static assert on that. So kind of the existing wording, this existing semantics mean that inside the body, those are just regular values.
Yeah, but you could still do if constexpr is constant expression, right? You could just do the same thing.
So the question was, could you just do if constexpr is constant expression? Not quite. The reason is that that would always be false, because that's not a constant expression in the body of a function. In C++20, we're adding a new functionality called isConstantEvaluated, and I'll get to that a little bit later and explain why it also can't solve this problem. So kind of hold that thought, and a little bit later, I'll talk a little bit more about that. Okay. So where is this in standardization right now? First, let's talk about kind of how the committee works, to give you just a little bit of context here. Before each meeting, we meet about 3 times a year, and before each meeting, everybody sends in all of their proposals in paper form. And this gives people kind of some time to read over the papers, to think about them, and in general, we don't discuss things at the committee that don't have a paper. We discuss papers in between meetings through email lists to kind of answer some questions, but sometimes that kind of has lower throughput than we would like, which is why we meet, and we're a member of ISO, so we have certain ISO rules to follow, which basically says that we have to be at an actual convened meeting to make certain types of decisions. So at the meeting, we discuss papers and we vote. Everyone in the room gets 1 vote, but you are encouraged to not vote if you haven't been following the discussion or if you don't understand. And the way that the voting works is we vote strongly in favor, neutral, against, or strongly against. Typically, we require at least a 2-to-1 vote in favor of something for it to move forward. The idea here is we don't just want a simple majority. We don't want 13 people to say yes and 12 people to say no, and we say good enough, move it through. We don't want things getting by on a razor-thin margin. Because if you can't convince at least 2/3 of the room that your proposal is a good idea, that might be a suggestion that you should work on it some more. Talk to the people who voted no, understand their objections, and see if there's a way to kind of improve things, address some of their concerns, something like that. So we have a very strong consensus-based model. Sometimes the design changes at the meeting. We try to not do that, but sometimes we do. The idea instead is that if we decide we don't like this design, this other design seems really promising, the answer is, okay, write a paper and we can talk about it next meeting, because maybe there actually is a subtle flaw in this design that we didn't realize. We don't want to be voting on something that we haven't had time to think about. So for this paper, the standardization progress, it was discussed in EWG, which is the Evolution Working Group. That's the group that all new language proposals have to go through last year in June. We voted not to merge the original version of this paper into C++20. On that vote, I actually voted neutral because I didn't feel like my paper was quite developed enough to say, yes, vote on it, put it into the standard, ship it. I was more looking for feedback to make sure, like, is this the right direction? Do we like kind of the general concepts? How can we make it better? So we also took a vote of encourage more work in this direction. We like the way this paper is going. And for that, it was 27 in favor and 4 against. So it was pretty strong encouragement of, try to solve this problem with something in this area. So related work. What other things are coming in C++20? What other proposals have we had? What are the things that this feature is commonly compared against? One of them is const eval functions. This was added in C++20. It's really similar to constexpr, but it requires that the function is evaluated at compile time. Remember that constexpr on a function means potentially evaluated at compile time. It's at compile time if it's possible and if it's required. Const eval says, no, this must be evaluated at compile time or it's an error. It's similar to the meaning of constexpr on a variable. These functions do not exist at runtime. So this means it does not help if only some of the code is compile time. For instance, indexing a tuple. When you index into a tuple, the tuple value could be a runtime value. You don't know the contents of the tuple, but you know its size, and you know the index you're using. So if we tried to use const eval to implement this, we would say you cannot index a tuple that has a runtime value. And that's not right. You can't use it to add static assert into an array, again, for the same reason. And also because the parameters themselves are still not compile time constants within the function. So const eval actually solves none of the motivating examples in this paper. It's a reasonable feature. It has lots of problems that it solves, just not these problems. You cannot overload a const eval function with a non-const eval function where that's the only difference. You have to use just regular overload resolution, and it's either const eval or it's not. And I mentioned you cannot use the parameters of a const eval function as compile time constants. So is constant evaluated? This kind of gets back to your question a bit. Is constant evaluated? It has many of the same problems as const eval because it requires the entire statement to be a constant expression, a compile time constant. So is constant evaluated is saying, am I using this code in a context that requires a compile time constant? So if you say static assert some constexpr function, then is constant evaluated is going to be true in there. But if you say int x equals some constexpr function, is constant evaluated is going to be false in there. It's based on how you use the result, not based on whether the inputs are known at compile time. And that means that we actually don't have the same kind of fine-grained control that constexpr parameters give you. So kind of here's an example. If we go back to that inverse function that accepts a double and returns a double, and if you pass in 0, it throws. So how do you solve this problem with this constant evaluated? Is constant evaluated, what do you do there? There's nothing you can do, because you don't know the value of x at compile time. Even if you do, you can't access it in a way that's at compile time. You can't put a static assert in there, because double x is just a regular old double, as far as the compiler is concerned. Whereas if we had constexpr parameters, you could say maybe it's constexpr, and if it is, static assert false. Now it doesn't matter how the caller uses the result. You still get a compile error. Does that kind of answer your question, or are you still confused?
Maybe we can follow up.
Okay. Okay. There's another proposal, parametric expressions, by Jason Rice. It's P1121. It's a proposal that he's working on that introduces the concept of hygienic macros. So this would be a sample syntax. It'd be a new type of function that has macros that are properly scoped and are complete units of code. Supports evaluating exactly once or 0 through n times, depending on the syntax you use. And he actually does propose allowing constexpr parameters on his parametric expressions, but only for parametric expressions. It solves many of the same problems, but not all. But it creates yet another shadow world. So now, in addition to regular functions, constexpr functions, template functions, and macros, we'll have parametric expressions. We'll have 5 ways to write a function in C++, none of them quite solving all of the problems perfectly. It would not replace existing functions. The body is always inline, like macros, which you sometimes don't want. It doesn't support overloading. It requires deduction of the types. So, like, overall, I think that this is kind of the wrong direction, even if it happens to solve some of the same problems, because the principles are wrong. So now let's get to the syntax, the maybe constexpr syntax in particular. Strawman, constexpr, strawman in this presentation. So these are some possibilities. Constexpr. This was my first thought. Const eval, when it was first proposed, was constexpr with an exclamation mark at the end. But there are lots of questions like, how do you pronounce that? Is it constexpr? Not. Like, that isn't quite what we wanted to do. It would be the first example of a keyword with these like other tokens in it that aren't just alphanumerics. So strike that. That was my original idea, but I don't think it's a good idea anymore. What about maybe constexpr? That's what I've been calling it this whole presentation. Seems like a good use of the value. But there's another idea. First, we need to go back to our principles. Our principles are consistency. We want to make sure that we have a consistent set of rules. Not just a set of rules that are complete, that cover all of the use cases, but that are the same thing everywhere. So let's look at what constexpr and consteval mean today. Constexpr on a variable means must be done at compile time. Constexpr at a function means done at compile time if necessary, usable at compile time if possible. But consteval on a variable, not allowed. Consteval on a function means must be done at compile time. Now, I noticed an asymmetry in this table. So what if we were to change it to be this? We would change the meaning of constexpr on variables to say, done at compile time if necessary, usable at compile time if possible. So a constexpr variable would become a maybe constexpr variable. This is an interesting property that existing code does not change meaning, because we know all uses of constexpr variables are initialized by compile time constants. But it gives us this nice symmetric table where we can actually simplify our rules down to this. This is really easy. Constexpr means maybe, consteval means definitely. This is what we have today. This is what we could have. It all comes down to how do we want to program. Are we Discordians? The comment was, oh yeah. Do we want to drive on the left side of the road if we're a semi-truck on Friday? Because nobody really drives on Friday anyway, so it doesn't matter. Maybe the reason nobody drives on Friday is because there's semi-trucks driving on the left-hand side of the road. Maybe if we fixed the rules, we would find out that actually this whole time we've been wanting to drive on Fridays and we've been avoiding it because it was dangerous. Or it was too hard, or too confusing, or some of us could do it and other people couldn't, and the people who couldn't didn't really want to ride with people who could because they actually couldn't, they just thought they could. Like, I think syntax is really important. I think that form follows function, but function follows form. The way that we write things determines the way that we think about things and the way we express ourselves. Do we care about consistency? So I'd like to leave you with a quote by Bruce Lee. I'm paraphrasing. Before I learned the art, a parameter was just a parameter, and an argument just an argument. After I learned the art, a parameter was no longer a parameter, and an argument no longer an argument. Now that I understand the art, a parameter is just a parameter, and an argument is just an argument. Thank you. Any other questions? Yes?
To understand the example correctly, then the std get would have to be a const eval as well as having constexpr index.
Okay, it's pretty far back. So the question was std get. Would that have to be const eval in addition to a constexpr index? Is that what you're saying? No, it wouldn't. So if we were to mark std get as const eval, then that would mean that it must be evaluated at compile time, which means that all of its arguments must be compile time constants, which means that the tuple or array that you're indexing would have to be a compile time constant. The only thing that we care about is that the index itself is a compile time constant. We don't care how you use the result. We don't care about the compile timeness of the thing that we're indexing into. So std get would remain constexpr as it is today, and then the index parameter would be marked, or we would create a bracket operator that does the same thing as std get and make the index a constexpr value. Yes?
This might just be me getting confused, but it seems that if we're moving template parameters out of the angle brackets into the actual parameter list, then in the prior days, those values were part of the type.
Mm-hmm.
Now we have then some parameters that become part of the type and some that don't, or how does that operate?
What do you mean part of the type? Like the function template type?
Yeah, say for instance in your bounded integer,
Yeah.
it seems to me that you could move your range of bounds into the parameter set under the new.
Okay. So the question was like basically what happens to the template parameters on class templates, where right now they're part of the type. What do we do with them? I'm not proposing making any change there. And the reason is that those are actually serving a different function. They are parameterizing the type itself. You aren't thinking of it necessarily as a computation that returns a result. You're saying, this is an integer type from 0 to 10. You're not saying, I pass in 0 and 10 and I get back an integer type. That's not how we're thinking about it today necessarily. So the general idea here is that the template parameters, they don't need any storage. It actually is a different type, but it's part of the same family of types. Does that make sense?
Yeah.
Okay. Any other questions? Yes.
So you stated that the way compile time parameters would work is just like templates.
Yes.
But then you also stated that it would reduce compile time because it would reduce the amount of
Yes.
So how?
Okay. So the comment was that I stated that it would work just like templates, but it would reduce compile times compared to the current world. I expect it to have pretty much the same compile times as specifying an explicit template parameter. Where it saves you is when you start using things like HANA or MPL, where you're wrapping the value in a type so that you can use regular function syntax. Okay? I believe that is all the time I have, so I'll be here to answer a few more questions, but thank you all for coming.